Okay, welcome back. Uh, as I promised or announced this morning, we're gonna talk about something a bit different from what we have been learning. So we're gonna start discussing this class of problems called submodular function optimization. Okay. So the lecture 9 is about minimizing a submodular functions, and lecture 10 is about maximizing a submodular functions. Okay. And I had a recent paper about solving something called chance constraint programs, and we realized that there's a nice connection between chance constraint programming and submodular function minimization. And based on this connection, we got a really nice improvement compared to previous work, and I wanted to discuss that today. Okay, then what are submodular functions? We have a set of elements. So this is like if you imagine combinatorial optimization problems where E stands for the set of edges. And if you imagine the matching problem, we were picking a subset of edges which satisfy certain conditions. And in general, we can define any set of finite elements, and set function basically takes a subset of this element set E. For example, you can take two subsets A, B of the element set. And we say that the set function is submodular if it satisfies this condition. So the summation of the function values for these two subsets A and B is at least the union value and the intersection value. Then if this inequality is satisfied for all subsets A and B, then we say that the function is submodular. Okay? And perhaps this is relevant to many applications in practice because of the following equivalent definition. We say that so the function is submodular if and only if it has satisfies the diminishing marginal returns property. If you have taken economics 101, it's used in many places in economics, and it's defined in terms of submodular set functions this way. So we take two subsets, A and B, and A is a subset of B. So B is a larger set. And now we are taking some element that belongs to none of A and B. So we are adding a new element to B and A. Okay, and then we capture the marginal difference by adding this element to a set. So the left-hand side is a marginal return when adding this element to a smaller set, and the right-hand side captures the value for the larger set. Okay, so we get like higher increase for the smaller set than the larger set. And this is the marginal, the like diminishing marginal returns property. Let me draw a Venn diagram. So we have A and B. Now we are adding a new element E, and you can prove that for set functions, the first inequality, a function satisfying the first inequality is equivalent to satisfying the second set of inequalities. You can prove this. Okay, so let me actually give you more concrete examples. So you can take linear functions. So you'd have a set of weights for the elements. When you take a subset S, you just take the summation of the corresponding weights. It defines a submodular function. And in fact, a linear function is called modular. Another name for linear functions are modular functions. Okay. And also concave utility. What is that? What is that? So we take non-negative weights. You choose a subset of elements. You first take their summation of weights, and then you apply a concave function G. So whenever you add a new element, your utility will increase, but it increases in a concave way. They say it kind of imposes the marginal, diminishing marginal returns property for that. Third example is the coverage function. Okay, it's relevant to something called the sensor placement problem. So you install a sensor, and then you draw an area that can be covered by the sensor, and then you place another sensor, and draw the region which can be covered by the sensor, and then you measure the area that's covered by the set of sensor you place, and then if you um, draw figures, then you realize that like the area that were already covered by the previous placement is except for those regions you are adding a new kind of new areas like this. So this value will always decrease if you have placed more sensors. This is third example. And also success probability. So it's relevant to, we talked about the weapon target assignment for online bipartite matching. So like you have an enemy aircraft, and then I'm have missiles, and I launch this missile, and let's say there's a probability of destroying this aircraft. Okay, and I'm also assigning the second one, and I'm also assigning the third one. And the probability that this aircraft is destroyed is captured by 1 minus the probability that all missiles fail. That is the success probability. Okay, so the probability of success increases in a diminishing fashion, in a concave fashion, as you kind of include more weapons. Okay. And also graph cuts, like this is related to the minimum cut problem, like max flow in cut problem. So you have a graph, and you take a subset of vertices and measure the set of edges that cross this subset. Okay. You have a partition of the vertex set, and you count the number of edges crossing the partition. Okay. That is a cut. That is it's a submodular function. So far, we have talked about only undirected graphs, where when you have two vertices, and we didn't take into account the direction from one vertex to another vertex. But you can imagine a directed graph where the direction matters for a connection. Then you could have, when you take a subset, you could have edges, arcs going out from this vertex set, but you can also have arcs that are going in to the set. But the directed cut only counts the number of arcs that are leaving. And even this quantity gives you a submodular function. Okay. And the last example is from matroid. I haven't defined what a matroid is, but let's say we are given a matroid, and uh, I think it has to be so. Rank function is that when you take a subset S, its rank function value is the maximum size of an independent set contained in this subset S. It can be that you take a subset of edges, and an independent set corresponds to a tree that doesn't contain a cycle. when you take a subset of edges, what is the maximum size about 4s or something like this. Okay. Let me leave it at this point. So these are examples of submodular functions. So it can naturally capture some nonlinear properties of your problems, not just linear functions. And if you imagine utility, coverage, and success probability functions, and then you want to maximize such a function. So in economics, I want to, achieve maximum possible utility as possible. Okay. And for cut functions, as maximum flow min cut suggests, I want to decrease the number of edges going that are crossing the partition. So in that case, minimizing a submodular function is more relevant. Okay. So for this lecture, I'm going to discuss this minimization problem, and the next lecture we'll talk about the maximization problem. Any question? All right. There are many ways to explain this problem of minimizing a submodular function, but I'm gonna explain it in the context of the separation problem. Okay, which I think is perhaps might be more relevant to optimization people. That's what. But a disclaimer is that my explanation is not the most typical way of explaining these things. So it's so. Anyways, no, okay. Let's go one by one. So we look at the problem of minimizing a submodular function. So let's look at this equation 1. So we have this submodular function. So the question is, which subset minimizes the value of the submodular function? Okay, I want to pick a subset. But the thing is that when you have the entire element set, then the number of subsets is exponential in the number of elements. Okay, but it's not that we are enumerating every subset, which would take an exponential time. Instead of full enumeration, we want to pick on one efficiently that minimizes the possibly nonlinear objective function. So what we do is the following. So because it's a set function, we can define a function over the set of binary vectors. Okay. The way you do is the following. So any subset of elements can be represented by its characteristic vector. So you have E length vector, and for each coordinate that corresponds to an element, you take value 1, you assign a value 1. If that element is part of your subset, 0 otherwise. Okay. Conversely, any 0, 1 vector corresponds to a subset of elements. Basically, you take the set of elements whose values are 1. Okay. In that sense, you can define a function over 0, 1 vectors based on the set functions. And you can do the converse way. When you have a function over 0, 1 vectors, and you can define a set function. Okay. If you do this, the submodular function can be viewed as this kind of integer programming problem where the objective function is possibly nonlinear. Okay. Your decisions are out of the set of 0, 1 vectors, and you are choosing the one that minimizes this function. Okay. Great. Okay. So we have this problem, minimize f of x subject to x belongs to not z. Sorry, z belongs to the 0, 1 vector. So I have a nonlinear objective here. So let's make it linear by adding non-auxiliary variable y. So this is equivalent to minimizing y, subject to y is greater than or equal to f of z, and z belongs to 0, 1, e. Okay? This is a common technique to linearize the objective. So basically, my initial goal was to reduce the value of f as much as possible. But if you add this new variable y, and I have a constraint that y is at least f of z, then if you want to minimize this value y, then you need to decrease the value of f. So it has the same effect of minimizing the original function f. Okay, so in that case, if you define a set of vectors y, z, which satisfies these two conditions as you denote the set by q of f, then the problem is equivalent to minimizing y, where y comma z belongs to the set qf. And qf is called the epigraph in general because you look at this function f and you look at the region that are above this function. It is called an epigraph. This is not just for set functions, but it also works for like convex or concave functions or anything. Okay. So we have this function. We have this problem of minimizing y, where y comma z belongs to q of f. Okay. So now that we have a linear objective, y is a single variable, which is a trivial linear function. Now that we have a linear variable function, and we have this mixed integer linear set, not linear, mixed integer set, this problem is equivalent to taking the convex hull of this set Q of f. We saw this in this morning. So you can take this equivalent problem of minimizing this variable y, where the feasible region is taken from the convex hull. Okay? Great. And you can argue, this is not too obvious, but you can argue that this thing is a polyhedron. This is not too obvious, but you can argue that this is a polyhedron. So this is this problem, although your function f is nonlinear, but this convex hull is a polyhedron. This problem 4 is a linear programming. It is a linear program. Okay. So, and we talked about the equivalence between the optimization problem and the separation problem, and that was based on the ellipsoid algorithm. So, using that, we have a polynomial time algorithm. If we can separate, or we can solve the separation problem over the convex hull. Okay, so that's what we are going to do. So we're going to solve or consider the separation problem over the convex hull. Okay. And again, I said that the convex hull is a polyhedron. So, and in fact, we have a good understanding about the convex hull, and that's what I'm going to explain. Any questions so far? Okay, so to explain the description of the convex hull, we need to define this notion of the extended polymatroid. This is an important concept. So what is that? Well, you collect the set of vectors pi, which satisfies that. So this is the linear function, right? So this is the summation of the component, which is equal to pi transpose the characteristic vector for a subset S. So this is a linear function where you collect the set of you add the weights of the element for the set S. That's all. That's less than or equal to the function value of F for all subsets. Okay. So the extended polymatroid itself is a polyhedron. It's defined by 2 to the e inequalities. Okay. Now, if you take an empty set for S, the corresponding inequality is 0 at most f of empty set. Okay. So, well, you can argue that this is not too obvious, but the expanded polymatroid is non-empty if and only if the function has the value of the empty set is non-negative. You can argue this. Okay. It's possible that a submodular function has a negative value for the empty set, but we are interested in minimizing a submodular function or maximizing a submodular function. So we can always take away some constant given by the value of the empty set. Okay. This thing is also a submodular function. Because if you remember the definition of submodularity, f of A plus f of B, at least f of A union B plus f of A intersect B. So if your function satisfies this inequality, then subtracting a constant from all values also preserves submodularity. So you can see that f minus f of empty set is also a submodular function. And in particular, if you evaluate the function value for the empty set, it takes value 0. In terms of optimizing a submodular function, we can assume that the empty set has a value of 0. That's what we can do. Okay. So we're going to focus on this case, but all these discussions just go through even when your function value doesn't have 0 for the empty set. Any question? Okay. Go real slow. So we are ready to describe the convex hull of the epigraph. Again, the QF, remember that Q of F is a mixed integer set, y comma z, where y is a continuous value, and z takes a 0 value, where y is at least f of z. This is a mixed integer set, where but f of g is possibly a nonlinear function in G, but its convex hull can be described by first you replace the 0, 1 constraint by this bounds on the x variables. Now you're adding a bunch of inequalities, y at least f for pi transpose z. Okay, but you have to take all possible coefficient vector pi from the extended polymatroid. And again, extended polymatroid itself is a continuous set where pi is a e-dimensional vector, summation of e and s, pi of e, at most f of s for all S, subset S. So this is a continuous set, which is a polyhedron. So for every possible, every point from the continuous polyhedron, you define this inequality. Okay, this is convex hull. So this convex hull is defined by infinitely many inequalities. Okay, but I want a polyhedron to describe this thing. But in fact, maybe polyhedral description is not necessary. What we really want is that, so I wanted to solve this optimization problem of maximizing or minimizing y subject to y comma z belongs to the convex hull of Q of F. So what I really want is not a description of this thing, but a separation problem, an algorithm for the separation over this convex hull. So even though this is defined by infinitely many inequalities, as long as you can solve the separation problem over this set in polynomial time, then that gives you a polynomial time algorithm for this optimization problem. That's what we are going to explain. Okay. Any question? I guess this logic is can be a little bit tricky, but just recall what we discussed this morning. So we proved that by the ellipsoid algorithm, the separation and optimization are equivalent in polynomial time overhead. Okay, so then what is the separation problem? So given y bar, g bar, can you prove that y bar, g bar belongs to the convex hull? Or if not, can you return an inequality or separating hyperplane that separates this point from the convex hull? Well, you need to check. What you need to do is to check whether this inequality is satisfied. Okay, so given y bar, g bar, can you prove that there's some point pi where pi transpose z bar is actually greater than y bar? Okay, that is what we want to check. Okay. Then the separation problem basically boils down to computing the maximum value of pi z bar. And you compare it with y bar. Okay. And the maximization is done over pi in the extended polymatroid. Okay. Any questions? Again, I want to check whether the set of inequalities is satisfied. It boils down to computing the maximum value of pi transpose z. If it's less than or equal to y bar, then it means that all inequalities are satisfied. If the maximum value goes above y bar, it means at pi, the inequality, corresponding inequality is violated. That's what I'm trying to explain. Okay. So the separation problem is equivalent to solving this maximization problem. Okay, I'm given a vector z. Okay, and I take this linear function g transpose pi, and I compute the maximum value of g transpose pi, where pi is taken over the points in the extended polymatroid. Okay, so this is equivalent to the separation problem. So this is a linear program, right? So again, extended polymatroid is a polyhedron. Let me write down. Maybe I'm making you confused here. But again, extended polymatroid is given by the set of vectors pi, which satisfies this inequality for all subsets in E. Although there are exponentially many inequalities describing this polyhedron, but still this expanded polymatroid is a polyhedron. So you have a linear program with many inequalities. Okay. Again, how do you solve this linear program? Well, you can use a simplex method or the ellipsoid algorithm or the interior point algorithm that guarantees a polynomial time solvability. Okay? But in fact, for this class of problems, there's much faster algorithm, much more efficient algorithm than all these tools for linear programming. That's what I'm going to explain. And this can be done by something called a greedy algorithm. This is a different style of greedy algorithm, but I will explain what it is. Any questions so far? Okay. Let me recap the flow. Okay. So we have this problem one, which is the initial objective. I want to find the subset that minimizes the submodular function value. And this formulation, I've written this problem in terms of a problem over the set of 0, 1 vectors. I have an integer program. But now you can define this mixed integer set by linearizing the objective. I have a linear objective y. Now, if you do that, because I have a linear function in the objective, and I have some mixed integer set, then you can take the convex hull that gives you the same problem. Okay, so I have a linear function, and I have a polyhedron. So by the equivalence between the optimization and separation, this problem can be solved in polynomial time if and only if separation over this polyhedron can be done in polynomial time. And by this nice theorem, we have this description of this polyhedron, description of this set given by these many inequalities. Now, to find the one or check whether my given solution satisfies all inequalities, the approach is to compute the maximum value of the right-hand side, and you compare it with the given left-hand side. Okay, so the question boils down to computing the maximum value of pi transpose z, where pi is coming from the extended polymatroid. And that's here. Okay. Yeah. Uh, no. In fact, that's because you're taking a finite number of solutions for z. So if you imagine, if you fix z, then if you fix the g part, then the dimension of the set is 1. You can only increase the value of y, right? So it's like you have 2 to the n half-line segments. And if you take the union of 2 to the n half-lines, that gives you the convex hull gives you a polyhedron. That's okay. F can be any function, but and because you're taking only 2 to the n possible choices for z, it always gives you a linear. It's not about the structure of F, but it's more about the structure of the epigraph. Oh, that's a good question. But I didn't try to explain it, but any other question? Yeah. Right. Well, you assume that if you say okay, there's an oracle that gives you the function value. Let's say I can make a query about a specific subset because I'm having the entire set of function values the set can be exponentially large. So that's not efficient. But you are assuming an oracle, and you just that's. So I don't want so in that sense we don't have a full description of the convex hull either. We know that it's a polyhedron, but we don't have the full description because the function values are not given to us. And in fact, the algorithm doesn't really need that. Yeah, that's what. Yeah, yeah, it's related to matrix actually. So here, I think the Edmund when he introduced this notation, or this concept, this used to be the rank function of a matrix. And a rank function of a matroid is a submodular function. Now people have realized, or maybe Edmund himself also realized that any submodular function gives you this thing. Okay. So here's a correct explanation. So matroid gives you this concept, okay? And in fact, Edmund realized that any submodular function behaves like matroids, in the sense that if you define this kind of set, but if you imagine, if you look at this description, so this is a set of vectors. But when you define a matroid, matroid has this kind of down closeness property, meaning if you have any independent set, then it's all the subsets, including the empty set, are independent. But if you look at this description, let's say I have a vector pi. Okay, pi is now a vector. Now you can decrease their components. Okay, so reducing the component values, um, after that reduction, that vector should belong to the set, right? Because all these inequalities are limiting the upper bounds of the values. Reducing the component is not. So what I'm saying is this vector kind of corresponds to an independent set in a matroid. So this is a concept that extending the notion of matroid to the continuous setting. And you can take any submodular function, not just the matrix rank function. Yeah. Yes. 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 You're right. You're right. There's nice connection. So you can say, if you are given a matroid, you can always compute a maximum weight independent set from matroid. And so this problem is taking a maximum weight vector from our polymatroid, and the algorithm is also kind of great. It's a good question. Any other question? Okay. Let me explain a proof, and it gives you an algorithm actually. So what you do is the following. So let's say, assume, okay, so the set of elements E is enumerated as E1, E2, and En. So small n is the number of elements, okay? And I have this vector Z, and I order the elements, the components of this vector Z, so that G1 takes the largest value, and G2 has the next, and so forth. Okay. When the components are not ordered this way, you can shuffle the ordering of the element, the components, and can prepare this kind of a sequence, right? So, but for simplicity, let's do this. And in fact, once you have ordered the component this way, then your algorithm is pretty much done. So this is the main bottleneck. That's why we need E log E time. That's coming from ordering the coordinates. Okay, and I'm gonna explain how you find a optimal solution. Okay, so what I'm going to do next is the following. So I'm gonna define a sequence of subsets, a chain. So S1. So S1 is the element E1. Okay, and S2 is the element E2. E1, E2. Okay, and Si is the first top I element. You repeat, and Sn is has the entire set of elements. Okay. And then you construct your solution as follows. So pi1, pi e1 to be the function value of S1. Okay. And pi e2 to be f of S2 minus f of S1. Okay. And pi, in general, pi of ek, the case element, is the difference between sk and fs of k minus 1. Okay. Again, the algorithm is as follows. You have your vector z, and you order the coordinates of the vector. Once you have ordered your the components of the elements, then you construct this chain of subsets. By this construction, S1 is included in S2, and S2 is included in S2, and Sn is the largest set. Okay. We're adding one element by one. And then once you do this, you construct a vector pi, which is supposed to be an optimal solution to this problem. So this one has the f of S1. In fact, when your this function value has a non-zero value for the empty set, then you can subtract the value of the empty set. But for the second element, you have the difference between the second set value and the first set value, and so forth. If you do this, you can prove that this vector is an optimal solution to this linear program. And the proof is based on LP duality. So what you do is you can look at the dual of this, and you can also construct on optimal dual variables. And you can use the complementary selectness. You can prove that the primal value with this solution and the constructed dual solution has the same value. That will prove that the solution is optimal by the strong duality theorem. The proof is contained in the lecture notes, so let me skip it. But the algorithm to construct an optimal solution is just this. Isn't it kind of amazing? I guess so to find or to compute this optimal solution, you just need to make n queries. Okay, you don't have to go through all possible function values. You just take this n subsets, and if you ask for the values, their values amount to making n queries, that gives you this solution. Okay. So that is it. So again, by the equivalence between optimization and separation, we can turn this algorithm into an optimization algorithm for submodular function minimization. But in practice, it can be much more faster. So what you do is you start with this linear program where there's no constraint and you have a single variable in the objective, and you separate one inequality by one, and the separation can be done by solving this problem with this efficient algorithm. And you add an inequality to your description, add a cut, and you solve that LP, and you get a solution and solve the separation problem using this greedy algorithm. And if there's a violated inequality, you add it, and you resolve that LP, and you repeat. And this approach is actually really faster, quite fast. That's what you do. But in terms of computational complexity, this gives you a polynomial time algorithm. And in fact, even though the ellipsoid algorithm takes the complexity, it's not known. So it's not known that there's a strongly polynomial time algorithm for a general LP. But for this class of submodular function minimization, there's a strongly polynomial time algorithm. But later on, these people came up with a combinatorial algorithm for solving submodular function minimization that do not rely on the ellipsoid methods. And I guess these two papers got the Fulkerson Award for this contribution. So this is one of the major areas in the community. Any question? Okay. Next, the second part is about something called chance constraint programming. And I found the connection between submodular function minimization and this problem. And I'll refer to one of my papers later after this lecture, so they can find more interesting materials there too. But let's talk about something easier. So we have an inventory planning problem. Okay, this is the simple problem. So what it is a retailer has to prepare some amount of items before the market opens. It's not that you observe the demand first and decide the quantity, but it's you prepare first and you wait for the demand. So it's possible that your stock value is smaller than the demand or vice versa. Okay, this is the thing. But the thing is that the demand value is stochastic. It's a random quantity. Okay, so and there's a cost of buying items. So I mean, if you want to, let's say demand is there, even though it's stochastic, if the cost of buying or preparing items is low, then you can just prepare a lot of the big amount, large amount, to prepare against this stochastic demand. But when the cost of preparing, securing, ordering items is high, then having a large amount of items can be expensive. So we need to kind of consider these two aspects. But what we assume is the following. So we assume that there are a finite number of possibilities for the random value. Yeah, so the B, you can imagine that this B is a random variable, and the possible outcomes for this random variable has this n possible values. Okay, and I assume that if there's a probability distribution governing this random variable, so the B takes value bi with probability pi, and I assume that the probability distribution is known to me. So maybe like you have a large amount of historical data, And based on the data, you can construct an estimated distribution, and that gives you these probabilities to me. Okay. And this is an example of stochastic programming problems. And in the literature, we say that each realization value, like BI, has a scenario. That's the terminology that's frequently used in stochastic programming. Okay. All right. So the purchase decision, it has to be based on the distribution of the stochastic demand. So your first attempt is a robust approach. That is, you look at all possible realizations of the stochastic demand. What you do is you prepare the maximum. So you prepare against the worst case scenario. Okay. The worst case scenario happens when this maximum possible demand occurs. So now my decision is to target the maximum possible demand, and I prepare at least that amount. You can do this by imposing these inequalities. So I has to be greater than or equal to every possible demand value. Okay. So this is called the robust approach. When you stumble upon this terminology of robust optimization, it means that you are targeting the worst case value. Okay. But it can be too conservative. So we know the distribution of the stochastic demands. Maybe the worst case demand values has like 0.1% of occurrence. It's possible. Right? It's just kind of an outlier. So let's say there's an outlier value. Somehow maybe there's some disruption going on. Then we might observe this large amount of demand, but the probability of occurrence is too small. Then does it really make sense to target this worst case value? Maybe not. Maybe we are targeting maybe the middle, the expected value, or like top 10%, and maybe like for 90% you are good, but let's say we are losing something for only 10% of chance. Maybe that's still better. Okay. That's the motivation for this something called chance constraint programming. So let's look at this formulation. So what we do is, instead of satisfying the demand for every scenario, what I impose is that I want to satisfy the demand with probability at least 95%. Okay. So this is the probability because B itself here is a random variable. Okay. So this is called the chance constraint program. So I got into this problem because, I started working on this problem like 1 month before I graduated from my PhDs. And the reason why I got into this problem was that I found a nice connection to integer programming. And let me explain why it is the case. So basically, the probability of satisfying the inequality has to be at least 90%. Then equivalently, the probability of failure has to be at most 5%. Okay, it's equivalent to that. And I can, compute the probability of failure by decomposing the random possibility for B into these n possible scenarios. It fails if my random variable B is BI, has value BI with probability PI. If Y is less than BI, I fail with probability PI. Something like this. You can imagine this. So I can model this. It's okay. I have this indicator function to indicate whether my stock is less than the demand for the I scenario. It takes value 1 if I fail. It takes value 0 if I satisfy the demand. I can model this indicator function with a binary variable gi here. Okay, so it has value 0 if I satisfy the demand. It takes value 1 if I fail. Okay, I can have this random the binary variable. Then you can set this. You can take this binary linear program to equivalently model the problem. So basically, here, if you take this thing, y is at least bi times 1 minus gi. If gi is 0, then y will be bi. So I satisfy the demand. If gi equals 1, then the inequality becomes y at least 0. So it doesn't do anything. And here I collect the total probability of failure that's bounded above by 0.05. Okay. So okay, just to summarize what we've just talked about. So we were talking about this chance constraint programming. So we have this demand satisfaction problem. My goal is to determine the quantity that satisfies a random demand with 95%. And what I just explained, which can be a bit technical, but just believe me that that problem is equivalent to solving this binary linear program. Okay, I have one binary variable for a scenario, and because I'm assuming that there are n possible values, so I have n binary variables. Okay. Okay, so this formulation is known a long time ago, and what people have noticed is that okay, you solve this integer program with a branch and bound framework using software, but then when these values bi's are large, okay, then it takes a long time to solve. It is known to be a difficult problem. Okay. So what people have noticed is the following. So can we add some strong inequalities to strengthen this formulation? That's what people have been trying to do. That's based on looking at this set of solutions satisfying this. So we take these binary constraints and these inequalities, and just forget about this constraint to limit the failure probability. So we just focus on the set of inequalities and the binary variables. Okay, and so we look at the set of solutions satisfying those constraints, and there's a special name for this. People call it this set as the binary mixing set. Okay. And this thing is now you take these inequalities. This is equivalent to y at least bi times 1 minus ei for all I. But if you take the maximum of the right-hand side over all I, and this is at least equivalent to y at least max I bi 1 minus gi. Okay. Now I define the right-hand side as a function of some binary variable z. Okay. Then this binary mixing set is equivalent to the epigraph of some function f. Okay. And what do you do? Well, you can prove that this function gives you a submodular function. Okay. So this is a submodular function. Let's go back to our discussion for the separation problem. Well, when you have a submodular function, then the convex hull of the corresponding epigraph is given here. And it's defined by this kind of inequalities. Okay. And the separation problem can be solved by solving this linear program. And you don't need a complex LP solver for this. You order the coordinate of a vector, and you take these values, and that gives you an optimal pi. You take the pi, and the corresponding pi gives you this inequality. You add it to your system. That will be cut. What I do is for this function f that can be shown to be submodular, you solve that separation problem, and you add that cut into this formulation, and you resolve this. And this, can expedite your, the branch and cut solver by, let's say, 1,000 times. That was the result. So that was the result. Just to summarize, so that's what I just explained. Okay, so you solve this LP relaxation, but you take out the solution y comma z, but for that y comma z, you take into account this modular function, and generate a cutting plane and edit, and you resolve that LP, and you continue, and that gives you a solution. All right. Is there any question? Okay. I stop early, and we meet, let's say, 3:20. Okay. We start 10 minutes earlier than the usual time. I guess if we end early, then we stop early. Next.